Number 5, energy distribution. Now the axis here will be energy and portion of particles that have certain energy, right? So, and then there are two curves. What we have to remember is this curve on the left represents the distribution at a lower temperature. If we heat up the particles, we give them more energy and all that, the curve will actually be represented like the one on the bottom, higher temperature, right? The difference, the peak will be located to the right side, but the peak will be lower. So they want us to figure out the most probable energy at the lower temperature. So we will refer to this curve, the curve on the left, and the one that has the highest portion is at this point. Right, that means the highest portion of particles having a certain energy at a lower temperature is located at this point. And this portion of particles will have this amount of energy here. So figure out that this curve is for the lower temperature, and then understand that this peak is where most of the particles have that particular energy. Okay, which is this energy here. Number 6, which elements have chemical bonds of the same type between their atoms? This is very important. It's between their atoms, not between their molecules. So aluminium is metallic. Phosphorus, P4, this is a phosphorus molecule, but between their atoms we are actually talking about covalent bonds, right? Not intermolecular attraction and all that. It's covalent bonds between their atoms. So metallic and covalent, we don't have the same chemical bonds. Chlorine, Cl2, argon, noble gas, is only monatomic, Ar. For chlorine, between their atoms we have covalent. For argon, because it's a noble gas, it exists as individual atoms, it is actually van der Waals forces. So covalent for chlorine, van der Waals forces for argon. Magnesium, metallic. Silicon, giant covalent, so covalent. Okay. Similar structure to the diamond, tetrahedral repeating structure. Sulfur is actually S8, and each bond between the atoms is covalent. Chlorine, Cl2 again. Okay, and the bond between the atom for chlorine atoms is also covalent. So sulfur and chlorine. Ethanol, boiling point 78 at these conditions, 101 kilopascals, the vapor doesn't perfectly obey the gas equations. In other words, it doesn't really behave like an ideal gas. It is another way of saying that it has high attraction force or strong attraction force among its molecule. And why so? Right, you have to recall that ethanol has a hydroxyl group where the H is directly bonded to oxygen, electronegative oxygen. It will allow one ethanol molecule to attract another ethanol molecule using hydrogen bonds. Alright, so for covalent molecules, hydrogen bond is a relatively strong attraction force. So having strong attraction force will make it behave not like an ideal gas. So there are intermolecular attraction force between the molecules of ethanol vapor. Okay, because for ideal gas, some assumptions is that they will have negligible forces of attraction among molecules. Reaction between sulfur dioxide and oxygen. What happens when the pressure of the system is increased? So first of all, the pressure. Increasing the pressure will make the gas particles become closer together. So we will actually increase the concentration. And when concentration increases, the rate of reaction will increase. Okay, so rate of reaction will increase due to increase in concentration. The gas particles get squeezed closer together. And when the pressure of the system is increased, right, the system will actually try to react by removing the added pressure. And how it does that, it will look for the direction where there is actually less gaseous molecules. We have 3 on this side, 2 plus 1. We have 2 molecules on this side. So increasing the pressure, the system wants to reduce the pressure, and it will look to create more sulfur trioxide. Right? It will remove the 3 molecules and try to form 2 molecules of gas, thus relieving the pressure. So equilibrium will move to the right. Dicarbon monoxide. One carbon joined to another carbon joined to another oxygen. All bonds are double bonds. And there are no unpaired electrons. So how might it look like? Okay. So we have this basic structure C, O, and they say that all bonds are double bonds. So we will make this double bond. Then we check how many unused electrons, or how many electrons are unused for bonding. Just focusing on the outer electrons. Carbon has 4 outer electrons. It has already used 1, 2. There are 2 more that are not used. They will be our paired electrons, because they say that whatever is not used will be paired up. This carbon has 4 outer electrons. 1, 2, 3, 4. All 4 are being used for bonding, so no electrons left over. Oxygen, group 6, 6 outer electrons. 1 used for bonding, 2 used for bonding. So we have 3, 4, 5, 6. Right, 4 that are not used for bonding. So number of lone pairs: 1 lone pair, 2 lone pairs, and 3 lone pairs present in this molecule.